Alright, section 5.3, scientific notation and significant digits. Scientific notation should be relatively familiar. Significant digits, well, if you've taken chemistry, you've probably seen it. If you haven't, well, you'll see it today for the first time. How do we use scientific notation and significant digits? Here we go. In scientific notation, a number is expressed in the form m times 10 to the nth power, where 1 is less than or equal to m is less than 10, and n is some integer. So you're basically going to reduce the number to some power of 10 times m. M will be between 1 and 10. It won't be less than 1, because if it's less than 1, you can go to a lower power of 10. If it's greater than 10, you can go to a higher power of 10. The digits in m should all be significant. A significant digit of a number written in decimal form is any non-zero digit or any zero that has a purpose other than placing the decimal point. So a significant digit basically has something to do with its presence in the number. It's important. It has to be there. And it's similar to rounding because you're going to want to round it to the appropriate number of significant digits. The more significant digits, the more accurate an approximation is. When you multiply or divide measurements, their accuracy limits the accuracy of the answer. So this is the key part. When approximations are multiplied or divided, the product or quotient should have the same number of digits as the least accurate factor. So that's kind of how this thing works. Alright, so here are some examples of significant digits. The number 26 has two significant digits, the 2 and the 6. The number 26.0 has three significant digits. The reason it's 3 is because the point 0 tells the reader that it's not just 26, but it's exactly 26.0. You wouldn't have to put the point 0 there, so therefore it is significant. On the other hand, the number 260 is only two significant digits. The last 0, we don't know if it's exactly 260 or just a rounding to 260. If we move to 265, now we have three significant digits. Back to 2600, again, the two zeros tell us that we only have two significant digits, 2 and 6. Finally, if we change it to 2605, we have four significant digits. So the first step to understanding significant digits is to understand how many significant digits each number has. Let's go to this screen. 0.26 has two significant digits. 0.0026 also only has two significant digits. And when you think about it, when you write it into scientific notation, you're going to only have a 2.6. That's where we're going to get it. If we stick a 0 after this, again, this 0 does not have to be there, but its presence tells us that it's going to be exactly 0.00260. It's just 0.0026. So this is three significant digits. 2600 is two significant digits, 26.0 is 3, 26.05 is 4. So these are examples from the previous screen. Again, count significant digits, because when you multiply or divide two numbers, you're going to use the number of significant digits in the number with the fewer significant digits. So when you're multiplying 2.6 times 265, since 2.6 has two significant digits and 265 has 3, your final answer should only have two significant digits because you're going to go with the lower number. So when you multiply that together, you get 689. You would actually round it to 690. Likewise, if you were multiplying 2 times 265, since 2 has only one significant digit and 265 is 3, your final answer should only have one significant digit, and you round 530 to 500. Now, in all honesty, significant digits is not that important for this math class. You can round to however many numbers you feel like it. For chemistry, it's much more important because of the accuracy of the things you multiply or divide by. So, not so important in this class, but you need to know what it is. Let's go to example 1. We're going to express this in decimal form, 2.7 times 10 cubed. So this is already in scientific notation. The 2.7 is between 1 and 10, and of course you have a power of 10. So whenever you use scientific notation, you're going to move the decimal point the number of exponent spaces to the right. So the 2.7 you stick a couple zeros at the end, 0, 0, and you move the decimal point to the right. So it would be from between the 2 and the 7 all the way out here. 2.7 times 10 cubed is 2700. I'm going to guess most of you are comfortable with scientific notation, so I'm going to be moving pretty quickly, and I'm not going to be that illustrative on these slides. Example 2. Express in decimal form 6.18 times 10 to the negative 7th. When you have a negative exponent, you will move the decimal point 7 spaces to the left, or the number of exponent spaces to the left for a negative exponent. So you will basically write all bunch of zeros in front of the 618, and that's your answer. Now you will notice that if you write the decimal point in there, there will be 7 1, 2, 3, 4, 5, 6, 7 spaces between the 6 and the 1 and where the actual decimal point is. And that's what you're going to find out. When you have the exponent is negative, it's going to be a decimal of some sort. Remember, negative exponent does not mean a negative number, it just means reciprocal. Example 3. Now we're going to express this in scientific notation, 3400. And what you're going to want to do is you want a number between 1 and 10. So you need to move the decimal point from there to there. So the answer is 3.4 times 10 cubed. The decimal point is going to go there. You have moved it 3 spots to the left, so your exponent is 10 cubed. So remember, 10 cubed is like 1,000. So 3.4 times 1,000. Alright, example 4. Expressed in scientific notation, 0.000041. And again, if you can do these, you don't have to sit through all this, and you can skip the examples you need to do. So to get the number between 1 and 10, you need to move the decimal space 0.5 places to the right. So there's the original decimal point. You need to move it between the 4 and the 1. Since you're moving it between the 4 and the 1, you need to have a negative exponent. So your answer is 4.1 times 10 to the negative 5th. And again, if you move the decimal point to the right, you're going to have a negative exponent. Remember, negative exponents suggest the decimal. Positive exponents suggest a bigger number. Let's go to example 5. 7,920,000. Again, you're going to move the decimal point to get in scientific notation a number between 1 and 10. So it's going to be 7.92. Since you are moving the decimal point 1, 2, 3, 4, 5, 6 spots to the left, your power of 10 will be 6. 7.92 times 10 to the 6th. And again, you can check your work by counting the spots. Number 6, express 0.0050 in scientific notation. Now, you notice that this 0 does not have to be there. Its presence tells you that you need to put it in the answer. And this is where significant digits comes in. You aren't going to just write 5 times 10 to the negative third. You're going to write 5.0 because you want to express this number using the same number of significant digits. And that's where the connection is between significant digits and scientific notation. Your scientific notation number should have the same number of significant digits as your original decimal. So 5.0 times 10 to the negative third, you have to move it 3 spots to the right, so it's a negative exponent. Just because you have a 0 at the end, that's significant because it doesn't have to be there. It's easy to compare numbers expressed in scientific notation because all you have to do is first look at the exponent on the 10, and if they're the same, then compare the factor. So here we go. Example 7. Replace the blank with either a less than or a greater than sign. 3 times 10 squared to the cubed compared to 2.4 times 10 to the 5th. So let's expand this number to see what we get. Since it's a product, you can do 3 cubed times 10 squared cubed. So that's 3 cubed times 10 squared cubed. This becomes 27 times 10 to the 6th. Now we have to convert this to some number between 1 and 10. That's 2.7. We put one of the 10s here, so this number becomes 2.7 times 10 to the 7th. That is clearly bigger than any number times 10 to the 5th. So you compare the power of 10. Since this one's greater, you can stop there. You don't need to look at the factor anymore. Alright, example 8. Let's compare these two numbers. 2 times 10 to the second quantity to the negative 3 power versus 2 times 10 to the negative 2 power all to the third power. So, let's take a look at the number on the left first. With the negative exponent, we can take the reciprocal of the positive. So, this is the same as 1 over 2 times 10 squared all to the third power. Now we can expand the 3 by distributing it inside the product here. So that becomes 1 over 8 times 10 to the 6th, which is the same as 1/8 times 10 to the negative 6th power. 1/8 is the same as 0.125 to the times 10 to the negative 6th. We want a number between 1 and 10, so let's make this a 1.25, but then that makes this number 10 to the negative 7. So all I did was convert this exponent to a decimal using scientific notation. First, 1/8 times 10 to the negative 6th. The 1/8 is 0.125. The 0.125 is the same as 1.25. And then I took one of the 10s and borrowed it. So it's 1.25 times 10 to the negative 7th. That's the first number. The second number is 2 times 10 to the negative second all cubed. So again, you can distribute the exponent because it's a product. So it's 2 cubed times 10 to the negative second cubed, which is 8 times 10 to the negative 6th. Now, we can compare the two numbers, and it's pretty clear that because the 10 to the negative 6 has a higher exponent of 10, it's the bigger number. So we would rewrite it as 1.25 times 10 to the negative 7th is less than 8 times 10 to the negative 6. So the correct answer is a less than sign using the original numbers. So again, what you want to do is convert them both to scientific notation, and at that point it's pretty easy. Just take the one with the higher power of 10. If they're the same, then you compare the factors. Last one, find a one significant digit estimate of x where x is equal to that fraction. So when you do these fractions, you're going to want a one significant digit estimate. So the first step to do is convert everything to one significant digit, and you can do that by rounding. So the first thing you want to do is put everything in scientific notation. So convert each number to some power of 10. So 3.25 times 10 to the 0th. This is 1.212 times 10 to the 4th. This is 3.9 times 10 to the negative 2, all divided by 1.86 times 10 to the negative 3. The next step you're going to want to do is regroup the numbers. First, you're going to multiply the factors together, then you're going to combine the powers of 10. So you'll rewrite it like this. Using the commutative property of multiplication, I rearranged it so all the factors are here and all the powers of 10 are there. All I did was rearrange the numbers. This is the part where you now round. You can round the 3.25 to 3, the 1.212 to 1, the 3.9 to 4, and the 1.86 to 2. And then you just calculate this number there. You can now simplify the powers of 10. The top of the fraction becomes 10 to the second because you add the exponents together. You still have a negative 3 on the bottom. Now, you approximate it by taking this number. 3 times 4 is 12 divided by 2 is 6. 10 squared divided by 10 to the negative 3 is 10 to the 5th. So your one significant digit estimate of this fraction is 6 times 10 to the negative 5th. If you're given this question on a quiz, this is how you do it. Again, regroup the numbers into scientific notation, rearrange them so that all the factors are in one fraction, all the powers of 10 are in another, and then simplify and bring it back together in scientific notation. That's it for section 5.3. If you have any questions, please ask me using Facebook or an email.